Welcome to the last of this year's series of lectures from the School of Science and Engineering at Anderson University. My name is Rick Podor from in the school as a chemistry professor. And normally our dean, Chad Wallace, introduces the speakers, but he had to be at a meeting across town, and we said, you know, rather than you risk getting a traffic ticket, we'll handle this. He should arrive a few minutes late and be able to hear Lee's presentation. So I'd like to introduce Dr. Lee Van Groningen. He took his PhD from Michigan State University, and he's been at Anderson University for 5 years. So he's going on 5 years.
Yeah, this is my 5th year.
He is an associate professor in the math department, and his expertise is, besides math, is numerical analysis, and I have no idea what that is. I told some students today that I really got away from math as soon as I could. About 8 months ago, Lee said he finally grew up and got married, his wonderful wife Lindsay, and they bought a house together, and now he's stuck in central Indiana.
That's actually a very apt way to put it.
So.
Yeah, Rick, thanks for introducing me. Thanks everybody for coming out, for braving the storms and the winds outside to come here talk about math. As mentioned, my specialty is in numerical analysis. For those of you that don't know what it is, I'm teaching a class on it this coming fall. It runs every 2 years. Some of you should come and take it. I think there's a few people signed up for it right now. Essentially, numerical analysis is an analysis of the computer algorithms we do, so that we can go through and actually solve problems when we solve them computationally instead of solving them algebraically. We've got all of this power that's in our hands using a computer. Let's actually harness that and then analyze what we're doing with it. That said, I want to do something a little more accessible. So what we're talking about today is essentially the portrayals of mathematics in the media. Namely, animated math is better, Matt Damon isn't that good at math, Kevin Spacey is much worse. Going through there, you may get the references. If not, you will get them in like 5 minutes. So first, how are mathematics and mathematicians portrayed in the media? So right away, first thing, take 30 seconds, pick anybody you know that's a main character either in a movie or a TV show, and just first one that comes to mind. You don't have to say it out loud, but just, yeah. I mean, I saw a few people do that. That's not one I had, mainly just because I have not seen A Beautiful Mind and just because it's a few years older. A couple more recent examples. Numbers I'm not actually going to say much about just because I never watched it, despite it being a show about math. I just didn't find it that interesting. I just did not relate to the characters well. Hidden Figures obviously came out a year ago or this past year. Very good. If that was what came to mind, very happy with that. The Imitation Game from 2 years ago, essentially the story of Turing creating his Turing machine, which turns into the computer. That's fine as well. The Math and Hidden Figures and Imitation Game was fine. It didn't get overly in depth, but that's not necessarily what the story was about. However, more likely when I've talked to people about this, what normally comes up is Sheldon Cooper. And I know I got a few nods out there, that's the first thing that comes up, or if not Sheldon Cooper, anything from the Big Bang Theory. And from this comes something that just annoys me a little bit. In the media, in movies and TV shows, math is not represented well. As I have it say it up here, math and mathematicians are poorly represented. This is not me being bitter. I don't care about mathematicians being portrayed as nerds. We are. I've met way too many of them to fight that stereotype. It's a stereotype for a reason. It's a stereotype because it's true. There's a lot of my students in here right now. They will vouch for that. The bigger problem is, though, the math is either often wrong, and they'll have some of the math that's up there correct, so they obviously went through and thought about it, but they did not actually go through and direct it well, and what they actually say about it is incorrect. Or they take something that's a very interesting concept and dumb it down. And this gives off this idea that the math is not accessible. It's going through and it's something that's hard and we should just avoid it because it's not worth pursuing and it's not something we can go and access. And honestly, this is one of the great things from Hidden Figures. If I feel this way about it as a white male, coming through and seeing this as a minority female, how are you going to feel about this? If you're in math, let's be honest, the vast majority of math, white men, Middle Eastern men, Eastern Asian men. So going through this for other genders, for other races, I honestly see how it is. So this is just something I want to talk about, and that's what we're going to talk about today. Good examples of math, bad examples of math. We're going to start with the bad ones first before we get to the good ones. So some bad examples of math. So this first is from a movie called The Code Conspiracy, which may not be too familiar. Let's just go with this.
Doesn't exist, it's random. Oh, it exists. Yes, we just haven't found it. Here. Circle these primes. Is she in the order? No. Here, look. Prime numbers from 1 to 500,000. Arranged in a spiral. Now, can you see any order? It looks organic to me. There's a lot we don't know.
Okay, there's a couple things I want to go back to on this. Looking at this, this is the claim of the Lem spiral. The Lem spiral actually is a real mathematical concept. You start with the number 1, then you basically spiral counterclockwise and you highlight every prime number. What he actually said to do was the correct process to do it. Looking at this though, if you had to guess, black or blue, which one are the primes?
Blue.
And my question is, we should be able to tell, right? Because what do we know about primes? I mean, we know primes, basically spread out. It's like we know past 2, there's going to be no even primes. So is there any way we can just have like these large groups of either black or blue primes next to each other? You would have several. That'd be like having 8 prime numbers in a row. That is not the Lem spiral. A couple of other things to point out, which I think somebody noticed when they go through the first time. When he asked them to do this, what's the first issue there? Or even going counterclockwise. Yeah, normally it goes counterclockwise. This one's going clockwise. What else? Yeah, you circled 1. 1 is not a prime number. So there's one big issue with it earlier. And just one other thing that you can see, possibly if you caught it really quick. When he hands this to him and asks him to circle the primes, they're already circled. We did not trust the actor to actually know the primes, but he dutifully does his diligence and goes through and makes circling motions off camera. In fact, having this up, this is what the Lem spiral actually looks like. So with that, okay, from there, black or white, which are the primes? Black. You can tell, black is much more sparse. What do you actually notice about that other than it doesn't look organic? Yes, the key thing is what actually comes from it is you see all these primes essentially follow diagonal lines. The vast majority of them come in diagonal lines, and that's the pattern that get formed from this. Now the question is, what does that mean? We don't know. It was just an interesting thing that came up. So it's just a mathematical concept that's interesting that came up, but don't make it wrong. Don't prescribe these things to it that don't actually exist. Our next example, one thing that you may have seen when I talked about math in the media, Good Will Hunting. This is something that people will talk about. So I want to go through this the first real mathematical scene here.
Mod fx squared dx. So please finish Percival by next time. I know many of you had this as undergraduates, but it won't hurt to brush up.
Okay, one thing before we get further into this. Everybody caught that last line. I know most of you had this as undergraduates, so it won't hurt to catch up. So this is at MIT. This is a graduate level MIT class. If we go back in and just zoom in on the board, he talks about Parseval's theorem, which is what he's actually writing there is part of the proof of Parseval's theorem. Parseval's theorem is essentially in the idea of Fourier series. It's essentially, if I had to guess, this is a signal processing class. There's a lot of legitimate mathematics we can see on the chalkboard. You can't see a whole lot over there. We've got some sums. We've got sums of complex conjugates. We've got integrals. We've got norms in there. It's a lot of stuff that involves signal processing. All the math that's on the blackboard is correct. But now we're going to let the scene play out.
dx. So please finish Percival by next time. I know many of you had this as undergraduates, but it won't hurt to brush up. Thank you, Stephen. I also put an advanced Fourier system on the main hallway chalkboard. I'm hoping that one of you might prove it by the end of the semester. Now, the person to do so would not only be in my good graces, but also go on to fame and fortune by having their accomplishment recorded and a name printed in the auspicious MIT Tech. Former winners include Nobel laureates, Fields Medal winners, renowned astrophysicists, and lowly MIT professors. Well, that's all. If you have any questions, I'm sure that Tom has the answers.
All right, here's our problem. So going through, this is our advanced Fourier system that we're trying to solve in our graduate level MIT class. Going from this, the problem is, one, Fourier systems are essentially modeling other functions using an infinite series of either sine or cosine waves. Tell me how many sine and cosine waves you see up there. Absolutely nothing. This thing has nothing to do with Fourier systems. This is not an advanced Fourier system. What this is an elementary graph theory project. Going through this, so taking it, I know it's a little hard to read. The first thing it says is we need to find the adjacency matrix A for that graph. The adjacency matrix is namely the number of edges connecting each point. So your adjacency matrix A. So really I can think of this as from and to. So I've got my 4 points up there, 1, 2, 3, and then 4 up top. How many ways can I get from point 1 to point 1 in one step? There's none. There's nothing circling back. Namely, there's no points going from it to itself. How many ways can I get from point 1 to point 2? One. Namely, I can take, so if I've got, I can go from point 1 to point 2 that one way. I can't get from point 1 to point 3 in one step. That would have to take 2 steps. And I can get from point 1 to point 4 in one step as well. From point 2, I can go one way to 1, and I can go 2 ways to 3. 2 ways to 3, not 3 ways to 3. From 3, I can only get 2 ways to 2, and that's it. From 4, I can go to either 1 or 2, and that's it. That's our adjacency matrix. Which one did I screw up?
2 and 4.
2 to 4. Yes, 2 to 4. I was looking at this, I'm like, that's not symmetric. This needs to be symmetric. So before I say it's like, oh, this is easy math, and then I screw it up. So, but that's our adjacency matrix A. So that's the first part of it. Really, for this problem, I'm coming back to this. So for the first part of this, it's the adjacency matrix A. Really, it's just understanding what it's asking. It's not a hard problem, though. For part 2, so this is part 1. Part 2. Is the number of 3-step walks. So it's the same idea, but now if I start at point 1, it's like, well, how many ways can I take 3 steps to get back to point 1? Well, for example, here I know there's at least a couple of them. Namely, I could start at 1, go to 2, go to 4, go to 1. That's 1. I could go backwards with that too. I could go from 1 to 4 to 2 to 1. So there's going to be 2. The way we're going to find this is basically just take this matrix, and if I take that matrix and then multiply it by itself, that's essentially the number of ways I can get from a point to a different point and then come back to the same point. So that's going to be the number of 2-step walks. The number of 3-step walks is just going to be this matrix cubed. The number of 4-step walks would be the matrix raised to the 4th. The number of n-step walks is the matrix A raised to the nth. So this is just matrix multiplication. It's a linear algebra problem, and here at Anderson, linear algebra essentially is what comes in between Calc 2 and Calc 3. Or if you come in with Calc 1 credit, since we don't offer Calc 2 in the fall, linear algebra some people hit as a first semester freshman. Part 3, I'm not going to go through all this. I can teach you how to do all 4 of these steps. Part 3, it asks for the generating function. I can't even read that. For I think just the generation function, just trying to do it for all points going to I to j. Essentially what this is we create this function f of z equals the matrix a to the n times then just x to the n. And if we do this, then it's an infinite series. But if there's nice properties with this matrix, which this one will have, the sum of a geometric series, we can essentially write, as we learned in Calc 2 for series, the sum of x to the n is 1 over 1 minus x. We saw that for geometric series. We can do the same thing here for a matrix. It's just now we have 1 minus our matrix A, our adjacency matrix, and then times our variable z, and then take the inverse of that. So once again, we can solve that with Calc 2 techniques. The fourth part is the generation function for, oh, that's what it is, for walks from points. This is the generating function for walks from points I to j. That's the generating function for walks from points 1 to 3. So basically that's basically, okay, figure out transfer from part 3, take out this 1 point in the matrix. So once you know what this problem is asking, you can solve it using Calc 2 techniques and linear algebra techniques. So instead of this being a problem that stumped everybody in a graduate level math class at MIT, this is something I can teach you if you're a math major by the time you're halfway through your sophomore year. So once again, this is math dumbed down. In fact, let me get back to my talk. This is me doing parts 3 and 4 on the board outside my office, I want to say about 2 years ago. It's a little hard to see, but I worked out parts 3 and parts 4. This, let me move the mouse out of the way, is part 3. This is our generating function. Part 4 went from 1 to 3. You just pick out this one. So that would have been 2z cubed plus 2z squared over 4z to the fourth minus 2z cubed minus 7z squared plus 1. So it looks like it's an impressive problem. It's not. It's actually a fairly easy problem. Next, the one that gets me the most is the movie 21. Just because the movie 21 is based on this book, that mic's on, is based on this book, Bringing Down the House by Ben Mesrick, which is really just an interview with a member from the MIT blackjack team. When I first learned about this, it was a very, very interesting concept to me. Namely, it's this idea that you can use math and take what you know about math and then exploit what it gives you. And so there were these students at MIT that studied blackjack. And since it has a history, the probabilities change. And when that probability is actually beneficial to you instead of the casino, you can exploit that, put a whole bunch of money in there, and then walk away having made a lot of money. They did this for millions of dollars. And 21 is essentially now the movie that gets based off of that.
All right.
So here's our start.
Now, who can explain Newton's method and how you use it?
You can use it to solve nonlinear equations.
That's impressive. That's really good. I mean, I'm very impressed by that, especially since my class is called Nonlinear Equations. All right, now somebody tell me something I don't already know. Anyone? Bueller. Anyone? Bueller.
Newton stole it.
Sorry?
Newton stole it. Joseph Raphson published the same method 50 years earlier. If the start value is too far removed from true zero, then it fails.
I'm sorry, what's your name?
Ben Campbell.
Ben. So Ben Campbell suggests that Joseph Raphson was the original author of this method. Well, if that's the case, then why didn't he get any credit? Well, for one thing, Newton had a better publicist. And for another, after 1700, we know very little about Raphson other than the fact that he discovered the Kabbalah about 300 years before Madonna. All right, now, let's give Ben a chance for some extra credit, shall we? We're going to call this the game show host problem, all right? Ben, suppose you're on a game show.
This is the Monty
And
Hall
you are
problem.
given a chance to choose from 3 different doors, all right? Now, behind one of the doors is a new car. Behind the other 2, goats. Which door would you choose, Ben?
Door number 1.
Door number 1. Ben chooses door number 1. All right, now, the game show host, who, by the way, knows what's behind all the other doors, decides to open another door. Let's say he chooses door number 3, behind which sits a goat. Now, Ben, game show host comes up to you and says, Ben, do you want to stay with door number 1 or go with door number 2? Now, is it in your interest to switch your choice?
Yeah.
Well, wait. Remember, the host knows where the car is, so how do you know he's not playing a trick on you, trying to use reverse psychology to get you to pick a goat?
Well, I wouldn't really care. I mean, my answer's based on statistics, based on variable change.
Variable change, which is just asked you a simple question.
Yeah, it just changed everything.
Enlighten us.
Well, when I was originally asked to choose a door, I had a 33.3% chance of choosing right. But after he opens one of the doors and then re-offers me the choice, it's now 66.7% if I choose to switch. So yeah, take door number 2, and thank you for that extra 33.3%.
Exactly. People, remember, if you don't know which door to open, always account for variable change. Now see, most people wouldn't take the switch out of paranoia, fear, emotions, but Mr. Campbell, he kept emotions aside and let simple math get his ass into a brand new car, which is better than that goat you've been driving around campus. All right, everybody, that's the end of the day. Thank you very much. Your grading papers are down here at the end. You can pick them up on your way out.
Okay, I actually legitimately wrote down a list where this doesn't look that bad. I actually have an entire list of complaints I have about this scene. So we're gonna go through this. There's like 5 or 6 things for it. The first thing is, this is a class entitled Nonlinear Equations. I have never heard of a nonlinear equations class. We have linear algebra to deal with all of the linear stuff. Everything else is assumed to be a nonlinear class. So essentially it's just too big for that. So that was the first thing. I did not want to miss some of these things, so I am going to go back to my list. The next thing is, Newton did not steal Newton's method. Newton and Raphson did work on it at the same time. Raphson did not publish it 50 years before Newton did. Newton published it actually probably 5 years before Raphson did, but they published slightly different things. Newton came up with Newton's method. I mean, he didn't call it Newton's method at the time, he just called it some other method, and he called it something in Latin probably. Raphson published it 5 years later. Newton did his for polynomials. Raphson did it for more general functions. And it's actually occasionally called the Newton-Raphson method. So it's not like Raphson doesn't get any credit for it. A couple other things. When he talks about, for Newton's method, having the start value too far from true zero, so in case, just to explain what Newton's method is, Newton's method is essentially a root finding method. If you have any function or any combinations of function, Newton's method is a way to find where the zeros of that are. Basically figure out where your intercepts are, where you're crossing the x-axis. In fact, if I go through, I just want to get the blackboard in the background somewhere here where we can actually see it. All of these examples we have up on the board, I know they're hard to see. Let me see if I can get something where Kevin Spacey's not in the way. So like right in the middle here, this is the idea. This is an example of what Newton's method is. Basically, you pick a point, you follow then the derivative down to the x-axis, take that point, go back up to the function, repeat. That's what Newton's method is. So going through, to start too far away from true zero, it does not converge. That's incorrect. It depends. It's actually problem dependent. There are points on certain functions where if you start too far away, it does not converge. The point is what counts as too far away. For some functions, it will work no matter what. For other functions, it will never work. For other functions, it may work, it may not work. But Newton's method is a standard way of going through it, and it works 98% of the time. Also, the fact that Newton's method is up on the board gives me something else to talk about. He's got 6 examples of Newton's method up on the board. They're not labeled very well, but if that's the point, it's like, okay, I've got these 6 things that are at the board. We saw class ended at the point, and now he's asking his students what they know about it. Why would you ask them what you know on stuff you've spent the past 45 minutes covering? Like if I go through and cover series like we talked about there, it's not like I'm talking for 45 minutes about series, have several examples drawn up, then ask you, so what do you know about series? It's the stuff I've just taught you. Other things with it, so going from this, he goes next to the Monty Hall problem. Where does this fit in? Why are we going for extra credit on that? The Monty Hall problem is not a nonlinear equations problem. This does not fit in this class. Also, just with that, it is not solved with statistics. It is solved with probability. There is a difference. And also just the way they talk about it, where Ben's character mentions variable of change, Kevin Spacey, then mentions variable change, so they're not exactly sure in the wording. Also the fact that he starts talking about 33.3% instead of 1/3. It's very obviously 1/3 here because it's 1 in 3. And the only reason I bring that up is because he goes from 33.3 to 66.7 and says it's a gain of 33.3. Which, yes, you would say that if you're doing it to 1 decimal place, but it's just rounding error. And the only reason I bring that up is because it annoys me a little bit when we get to our 3rd clip. So we'll get there. That's my list of issues I have with the 1st clip. 2nd clip.
Study of the conditions for convergence of an infinite series and was concerned with developing the basic theorems of the calculus as rigorously as possible. Any questions? No? All right, moving on.
Isn't it true Cauchy stole from his students?
Yes, I heard that. What's your theory on that?
They say he used his students for their brilliance, then discredited them and stole their equations, stole their hard work.
Well, it wouldn't be the first time a teacher was accused of that. I think what he's referring to is Vladimir Stupnitsky, yes?
Okay. I'm not going to take this any further because Vladimir Stupnitsky is just an alias they come up through the course of the movie, so that does not matter. The things I want to point out from this, we're going back to accusing great mathematicians of stealing things. Obviously, it's just to prove this point in the movie. Let's just stop this. Newton didn't steal anything. Cauchy didn't steal anything. Stop accusing mathematicians of things like that. My other issue is the way they're talking about this. You heard him mention, working out the theorems of calculus. Based on what we had in the background, we had some continued fractions in the background. We're working on series stuff. My guess is this is roughly halfway through a Calc 2 sequence or something like this. When this random shadowy sinister figure shows up in the back of a class, how does nobody react to this? It's just all kind of like one person turns around like, oh, it's that weird guy that's never been here before, just coming up and telling these sinister things. That's my biggest rant with the second one. All right, the third one actually comes in the middle of the movie. This is when Ben first gets invited to join the team.
Oh, our honored guest. How you doing, Ben?
Okay.
You ever been in this room before?
Yeah. Organic chemistry in my freshman year.
How'd you do?
I got an A. Professor Rosa,
Mickey, please.
is there a problem with my paper?
Well, you found a more efficient method for finding true zero than Isaac Newton, and that, my friend, is not so much of a problem as it is a major ass-kicking. Although Newton has been dead for over 250 years, so it wasn't exactly a fair fight.
So there's some kind of a math club?
Okay, so the issue I'm taking with this again is we're going once again against Newton because we need to slander Newton as much as possible, apparently. Once again, everything they say, not that bad. This is the whole point I bring up is since Newton's method is finding roots, going through you need to be precise with this and how you do it because you get all, essentially with Newton's method, if you're going to do it with the computer, that round-off error will build up. So that was when I was upset about the round-off error with the probability. That round-off error is going to be upset. You're not going to find true zero very efficiently. Also, if you come in and ask about if there's a problem with your paper where you're beating Isaac Newton on something that is still used to this day, in the vast majority of computer algorithms that you have to find roots on it, you're using Newton's method. If Newton's method doesn't converge, you've got a backup using the bisection method. So this is something that's probably used in 95% of programs that involve root finding. If you can come up with a method that is more efficient than Newton's method, that is not a paper you turn in as a senior. That is a doctoral dissertation where you name where you want to go to work as a postdoc or essentially work as a professor. So it's just such a thing that's like, oh, is this something wrong? Like, no, this is something that needs to be published immediately so you can have fame and fortune. So those are my thoughts on 21. Just very, very hopeful with it, and then lots of problems with it. The other problem I have with 21, like I love the book when I went through and read it since this is a true story. I mean, I told my Calc 3 class with this. The first thing essentially they say in there, if you're going to go through and be on a card counting team, you cannot have white men. Vegas is suspicious of white men. You can pull this off with women. You can pull this off with minority men. You cannot have white men. So naturally, what's the first thing they do? Cast a white male as the lead. So that threw it off right away. All right, next, something that's not great, but something I consider a little more acceptable. So this is from The Hangover. Basically, the Rain Man scene.
belly, 10,000.
10,000.
Hey, these seats taken? Feel free. All right, let's play some blackjack.
I'm just going to pause it here because this is all I want to pull out from the scene. They're not doing anything special with math. It's just essentially we've just got random symbols. We've got some integrals up there. We've got polar coordinates. We've got, let me let this go for another minute or so. We get some sums that come in here. And that's all it is. It's basically just going through here and just being like, woo, math is magic. We don't know how it works. We're just going to throw a bunch of symbols at you and call it good. And at least for that, they're not getting it wrong. They're just being like, you know what, we're going to have some fun with this and just whatever. The card counting's not right, but I'm not going to complain about that. Card counting's actually really easy, and I could teach you the basics of it in like 5 minutes. Okay, so those are my bad examples of math. And now we're going to move on to some good examples. So namely, the place where we find good examples, cartoons. Hence the name Animated Math is Better. We find good mathematics in cartoons, specifically in The Simpsons and in Futurama. The reason it's in those two is they shared a lot of the same writers. And they had writers that were actually very good at math. Some of them actually had advanced math degrees. But this way they actually know the subject material, so they can actually bring it out instead of just trying to force it in ways. So for our first example from The Simpsons, this is just a clip. They had nothing special with this. There was no joke based off of it. This is just a clip at the Springfield Isotopes game. And it's just talking about the attendance of the minor league game. And for these, the numbers look random. D is basically there's not enough information to tell a question on a standard math exam. So it's like, yeah, on a standardized test with the math part, there's not enough information to tell. That's D. So right now it just looks like there's 3 random numbers of roughly 8,000-ish. Going through this though, those numbers aren't just random. For example, 8191 is a Mersenne prime. Mersenne primes are probably the most common way we find primes now that are unknown. Mersenne primes have the form 2 to the p, then minus 1, where p itself is a prime number. Right now, the 6 largest primes that we know are all Mersenne primes. The largest Mersenne prime, or the largest prime we know, was a Mersenne prime that was actually found last year, I want to say by somebody in Missouri. Basically, they just have all sorts of people on the internet that go through and just let their computer be used to search for these primes. The current right now, just because I wrote this down, the largest prime we know, well, first of all, 8191 is a Mersenne prime. It's 2 to the 13th minus 1. The largest Mersenne prime we know right now is 2 to the 74,207,381 minus 1. There are 22 million digits in that number. That's why we're using the internet and things to search for Mersenne primes. They need a better name for it, though. It's called the Greater Internet Mersenne Prime Search, or GIMPS. So 8191 is a Mersenne prime. 8128 is a perfect number. Perfect numbers are numbers where the sum of all of its proper divisors add up to the number. For example, 6 is a perfect number, because what are the divisors of 6? 1, 2, 3, and 6. Well, it's the proper divisor, so you don't count itself, so 1, 2, and 3. So 1 plus 2 plus 3 is 6. Those are perfect numbers. 8128 is a perfect number. At this, it's like, okay, this could be coincidence, just because we've got 2 large numbers and we had nice properties with them. But there's probably a lot of numbers around 8,000 that have nice properties with them. That coincidence kind of goes away, though, when you realize Euclid actually came up with this relationship. For every Mersenne prime you know, you can find a perfect number that's based off of it. So the idea that it's coincidental becomes really a lot of a stretch. 8208 then is a narcissistic number. Narcissistic numbers, you figure out how many digits there are in the number, and you take each individual digit, raise it to that number. So 8208, it's a 4-digit number. 8208 is equal to 8 to the 4th plus 2 to the 4th plus 0 to the 4th plus 8 to the 4th. So once again, it's this special number. For narcissistic numbers, there's actually very few of them. The first examples are obviously like 0 through 9 are all narcissistic numbers because they're all just raised to the first, so it's the same number. Other than that, the next one I believe is 153. 153 is 1 cubed plus 5 cubed plus 3 cubed. But then going with this, one of the reasons also narcissistic numbers are special, there's only 88 of them that exist. Mathematicians have proved. It's not like we're going to find one that's got 22 million digits in it. It's once you hit a certain point, which is at this point, it's actually more than, no, it's not. It's 10 to the 60th, so there's 60 digits in it. But once you hit that point, there are no more there, just because if you keep multiplying it to that high of a number, you're going to be way above where you need to be. But once again, this is one of 88 specific numbers. So we are actually pulling out a lot of things from that. Also with this, though, there's enough math in The Simpsons. Someone wrote a book about it. Namely, this is from Simon Singh, who's written a lot of stuff like on Fermat's Enigma, Fermat's Last Theorem. I actually went through and wrote a book on this, and there's 12 to 13 chapters, and they're just going through and covering all sorts of interesting tidbits like this. Also, this came out like 5 years ago, too, so we've got 5 more seasons of it because The Simpsons will never die. It is the longest running syndicated TV show by far. In case you're wondering how old The Simpsons is, The Simpsons came out like 10 months after Seinfeld. And Seinfeld's been off the air for nearly 20 years now. Okay, so that's The Simpsons. Futurama with Keeler's theorem is actually what I really want to look at, just because. So the Futurama theorem, aka Keeler's theorem. As far as I know, this is the only TV show that has actually gotten a mathematical paper published based off of it. This is an actual theorem that was proven in the show. So here's the idea. Basically, this was season 6, episode 10, Prisoner of Benda, based off Prisoner of Zenda, which I don't know, but that's the reference because, once again, you've got nerds writing the show and they've got all these weird sci-fi references. But basically, we have this mind switcher. People want to change, essentially, their experience. So it starts with Amy and the professor switching minds. And then throughout the course of the show, we have several people switching, including like a random robot king, sentient wash bucket, a bunch of other stuff. But the problem with the mind switcher is you can't switch minds back. So everybody gets stuck in these opposite bodies, and they need to figure out, okay, how many other people do we need to bring in to actually go through and get everybody back into their correct body? So this is the actual mathematical problem we're solving. Well, how many extra bodies are necessary to revert back? That's the solution, which shows up really terribly on my picture, which is why we've got it here so it's clearly. This is actually a screen clip from the show. This is the actual proof. We will come back to this in a second because I want to show you what the actual answer is. So the actual answer, anybody just got a guess on this of how many it would be, like based on the number of people there? The answer is 2. You can actually switch everybody back just by adding in 2 extra people. And we're going to go through this. So this is the actual proof that's up here that actually appeared in the show, and essentially this is what got published. I'm going to show you what all of this means. First, though, I need several volunteers. I know there's some Alpha Chi people here that are going to help me out. So other than that, I need 7 people. So just first, so how many do I have here? I've got, yeah, Lindsay, if you want to come on down, you'll be 7th. Basically, since I can't actually switch your mind and body, take a mind and a body. You need one of each. Just make sure you don't end up with the same number. Once again, everybody needs a mind and a body. Hold on. Hold on, Ashley, I'm taking this from you. You are going to be a helper. Lindsay's going to be a helper. Actually, hold on, let me switch you guys just because I want to make sure we've actually got a loop with this. So we've got this. Where did my other sheet go? I mean, very technical visual aids here. Actually, okay, so the first part. We can see this first. Let pi be some k cycle on n equals 1 through n. WLOG is without loss of generality. We write pi is equal to, and the key thing is here is we're saying, since it's doing essentially 1 through k, we're going to switch k bodies. We're just going to have a group of k people that are in the wrong bodies. Everybody else with this k plus 1 to n, they're in their right body. So we don't have to switch everybody. It's not like we'd have to go through the entire room to do it. So what we're going to do is we're going to line this up. And the key thing is we're going to line up 1, 2, and then 2 to 3. So basically I'm starting 3 and 4. What I need now, so okay, everybody body on the right. Okay, so the way I'm going to do this, since we've got mind 4, I need body 4. You need to go second. So as you can see here, I'm basically going to match up mind to body next. So body 5 is next. You're next. So we've got everybody lined up. The first thing we're going to do, so that's that. So this idea of let AB represent the transposition that switches, basically AB, those are the two people you throw into the mind switcher, and you're just going to switch their bodies. We introduced these two new bodies, X and Y, are two new bodies over here that we're going to switch into it. Helper 1 and helper 2. And then what we're going to do is it says for any I equals 1 through K, so basically somewhere in this, we have one person either start in the middle or at end, the other person's going to start on the far left. So the first thing I'm going to do, Ashley, I'm going to take you here. Basically, person on the end. Also, one thing I want to point out before I start switching, this person on the end will have a cycle. So basically, I could just move her over to the front if I needed to and just start and would still be the same. Basically, this would just be one circle that you're cutting into. So Ashley, I'm going to do is first time you have you here, switch with her on the end. So switch minds. And then you're just stuck there for a while. Lindsay, go through. You're going to start on the other end. So this is essentially what I've done. Is Ashley starting here at this Y, I plus 1. She's just starting at one point. Here it's just we're starting at the end, and she switches with the last. Lindsay's coming through here. She's switching with the first person. Okay, now we go through. Lindsay go through, and then she's got X2, so she switches with the second person. Switch with the second person. Mind. Yes, you only ever switch mind. As you can see now we've got somebody that's actually in the correct, has a correct mind in the correct body. Lindsay, then just keep working your way down. And this is going to go through then and switch correct mind into the correct body for everybody till the end. No, hold on. You guys don't switch yet. Because now what do we still need? Everybody's good except the start. So basically, you need to switch back in. That's where Ashley comes in after everyone's gone through. You can go through, switch with the start. And now just by adding in those two people, all of the initial 5 people are back in their correct body. We do have one issue, though. What's our issue? The people that we've helped right now, they're switched. This is the reason why I couldn't have them switch right away, is because once they switch, they can't switch back again. And so now then you would not have them switch yet if you had any other groups. Like if we had another group of 6 people over here, we'd go through and switch everybody there, because once they switch, they can't switch again at the end. So if they went through every time they do this just for one group, they end up switched. If they went through and did it for another group over here, they'd switch back and they'd be fine. But since now I'm done with my groups, now I can have my 2 helpers switch, and everybody's good. And that's how it'll work every time. You can break it down every time just into groups like that. So that's the proof. The basic idea of the proof is up there. Line every mind up to the next up next to the correct body. Have one person switch on the end. Have the other helper go through, switch with the first person, just switch all the way down the line, switching people into the correct body. Then at the end, essentially have that first helper go back, switch with the first person, and then if need be, have the helper switch. All right, thank you, volunteers. Sure. I don't know what I'm going to do with them, but thank you. Yeah, if you want to keep them, keep them. Also, so that's Keeler's theorem. Any questions?
Have you run across any other TV situations or movies that gave some good stuff?
I'm sure I have. It's not coming to my mind right now. There is plenty of good stuff out there. It's just, since I see the good stuff, I'm like, okay, also, being at the PhD level, you're like, okay, that's good stuff, but it's not at the level that normally intrigues me that much. It's most of the stuff I know, it's like, oh yeah, that's correct. After stuff I'm not sure, I'm kind of like, okay, I'll come back and look at that later. That's one of the reasons why I hesitated to put some of the stuff from numbers in there. It's just because there was stuff I don't know. But some of it I was very hesitant on. I remember, the start, they're kind of if you show me how a droplet of water hits the ground, I can actually trace back to it and tell you where it comes from. Well, I'm like, I don't know if you can do that just because it's based off the size of the water droplet, based off wind, based off change in elevation, things like that. But once again, I don't know that well enough to say that it's actually wrong. My biggest issue with numbers is okay, this is a guy that knows every idea in mathematics. You know how to do algebra, you know how to do combinatorics, you know how to do numerical analysis, you know how to do analysis, you know every different specialty. And that's just not realistic. But yeah, there's been a lot of places that, like A Beautiful Mind, I believe, had very good things. Some of the stories of Ramanujan, I believe, are correct, things like that.
We're just saying in Hidden Figures that like the main character was analytical geometry, but all the math they had her do was not at all.
Well, some of that's what I mentioned, yeah. I mean, she talked about having a specialty in analytical geometry, Taraji P. Henson's character. But with that, there was no actual analytical geometry that was going in there. Like when we talked about this, I won't say it's been out long enough so I can talk about the fact, like they use Euler's method. And that's her idea and how they go through and solve the main problem of going from an elliptical orbit to a parabolic orbit. Euler's method is not a special method. Euler's method we first talk about in Calc 1. I mean, it's not something we focus on in Calc 1, but yeah, once again, it's there. But it is a proper way to solve that problem. So yeah, they just didn't get into it real deeply.
A related question, do you think these guys, like the writers for Simpsons, insert that just for their own satisfaction?
Oh, I fully believe so. I fully believe this is like...
Somebody comes up and comments, that's fine, but it's not a...
Oh no, I don't think they're doing this to be recognized at all. I very much think this is for like inside jokes, and they can go through and look at it and just laugh at it and be like, haha, that's what we did. Once again, I mean, that's the kind of stuff I would do if I had the talent to write stuff like that. Other questions?
Later on in the movie of Good Will Hunting, when Will actually starts like working under that professor, they like go through kind of like proofs of problems.
Like that graph theory problem that supposedly they've been working on for like 2 years, where it's basically all the lines just connected in the graphs.
Yeah.
I don't know graph theory well enough. I would actually probably default to Dr. Lambright on that if I want to put him on the spot, but I'm not going to put him on the spot. I've read up a little bit on it too, just because it's that same one. That is a more difficult question than the one that they actually showed. But once again, they said that would not take 2 years. Going through that actually takes like a month to go through and cover all of the ideas in that. It would not take them 2 years to actually go through and solve that. So once again, that's a better level of mathematics. That's deeper, but still not as deep as they make it seem. Other questions? All right, thanks everybody for coming out. I hope you enjoyed it.